Welcome to Magnetism. We are going to start our new topic today, and we just talked about electricity, and it turns out magnetism and electricity are somewhat related. But before we talk about the relationship, we have to talk about what magnetism is. So we're going to go over magnets today. Magnets have two ends on them. We call them poles, and there's a north pole and a south pole. This might sound familiar to you from hearing about the North Pole and the South Pole on the Earth. It turns out that has a lot to do with magnetism. Just like electricity, where opposites attract and likes repel, magnets do the same thing. Like poles repel each other, and unlike poles attract. So, if you put two north poles next to each other, they are going to push away. If you put two south poles next to each other, they're also going to push away and repel. But if you put a north pole next to a south pole, they are going to attract and want to stick together. It's really interesting because if you have a magnet with a north pole and a south pole and you cut that magnet in half, you don't just get a little south piece and a little north piece. You actually get two whole new magnets with their own north and south poles. So, in this picture, we have one magnet with a north and south. And we break it in half, and then we have two magnets. And if we break those in half, we get four magnets. And they are all fully functional. This is why magnets are described as dipoles. So, the prefix di means two. So this word literally means it has two poles. A magnetic monopole, mono meaning one, has never been found. So scientists have never found a north pole or a south pole all on its own. They only ever find them in pairs, a north and south together. These north and south poles create what we call a magnetic field. And just like electric field lines, we can visualize magnetic field lines in our heads using certain rules. So magnetic field lines can be visualized using magnetic field lines, which are always closed loops. So anytime you have a north and a south pole, there's going to be a closed loop between them. And the first rule to drawing this is that they always start on the north and end on the south. So I would make my complete loop starting here, going all the way around and ending on the south. And because it goes north to south, my arrow has to point that way. Just like with electric fields, the more field lines we have, the stronger the magnetic field. So if I have three field lines on top here, but I have a whole bunch on the bottom, this wouldn't happen, by the way. They would be equal, but just to demonstrate, if I had a whole bunch on the bottom and just a couple on the top, the bottom would be the stronger magnetic field. And rule number 3 is that field lines never cross. Don't ever cross the streams. So, your field lines for magnets are always loops from north to south. If it's a strong field, it has more lines, and those lines will never ever cross. Now, just like with electric field lines, if you have more than one magnet interacting, the force felt between those magnets, either repelling them if they're likes or attracting them if they're opposites, is caused by that magnetic field. And you can actually draw the interaction between those. And that's what you're going to be doing for your homework question. Now, the Earth has a magnetic field. I already talked about north and south poles and how you've probably heard those, especially when talking about Santa Claus living at the North Pole. And the reason it's called the North Pole is because if you take out a compass, the north end of that needle will point north. Now, that's really interesting to think about because we have our North Pole and the north magnet is attracted to it. But our rules for magnets are that opposites attract. North shouldn't be attracted to north, it should be attracted to south. And it turns out that's exactly what it's doing. The Earth's north pole, or this part of the world, is actually a south magnetic pole. So if we were to imagine a bar magnet in there that has a north pole and a south pole on it, the south pole is actually what is up here. And that's why the north end of the compass is attracted to it. So it's kind of misnamed, but we've named it not after what it physically is, but by what an instrument tells us. That's why it's called the North Pole. Now, we can have other kinds of magnetic fields besides these big, long, loopy ones that are on bar magnets. We can also have a uniform magnetic field, which is constant in both magnitude, or size, and direction. So, if I have a south pole of a magnet, and I bring it next to a north pole of a magnet, the magnetic fields from these north and south poles are going to interact with each other. And when they interact, they're going to make a uniform magnetic field. You see that all of these lines are pretty constant both in size, how many we have, and the direction they're pointing in. So the closer you get to opposing poles, the more uniform your field is going to be in between them, in this space. Now, your homework question is to draw the magnetic field lines for the magnets below. So you have three different situations. You have one here, where you have a north and a south next to each other. You have another here, where you have a south and a north next to each other. And your third one is a north and a north next to each other. So, using our three rules about drawing magnetic field lines, and thinking about what kind of field you should have between these poles based on if they will attract or repel, I want you to draw me a picture of what's going on here for each of these.